Let's finish up chapter 4 with section 4.6, uniform integrability, the Vitali Convergence Theorem. So one last convergence theorem. This one doesn't really fit the mold of the others. This doesn't apply to a particular class of functions the way we kind of developed Lebesgue integration with a new class of functions and a new convergence theorem. For one thing, the Vitali convergence theorem will require a set of finite measure. When we had sets of finite measure, we had bounded functions. And the Vitali convergence theorem doesn't require that. It requires some integrability stuff, uniform integrability in particular, but sets of finite measures. So I can't really put my finger on the class of functions to which this convergence theorem will apply. It applies to some functions from all the classes. So this one's a bit different. This is actually an addition to the fourth edition of the book. This didn't appear, if memory serves, in a third edition of Royden's Real Analysis. So we'll introduce a new condition on a set of functions, this condition of uniform integrability, and this will allow us to prove a new convergence theorem. We need a preliminary lemma. Let's start there. Lemma 4.2 says, for E, a set of finite measure, we'll have a lot of that finite measure stuff in this section, and a given delta greater than 0, E is the disjoint union of a finite collection of sets, each of which has measure less than epsilon. So if you've got a set of finite measure, you can partition it into little measure pieces. Okay, what'll cause us a problem with this potentially is, well, finite measure doesn't mean bounded, and the rational numbers are an unbounded set and they've got measure 0. But the boundedness will has a potential to cause some problems. So what we're going to do is for each, say, natural number n, consider this set, E set minus the closed interval negative n to n, or equivalently E intersect the open interval from negative infinity to negative n union open interval from n to infinity. It's kind of the wings of set E. It's the stuff off to the sides in the distance when n is large. One thing, when n approaches infinity, this interval will approach the whole real line. This will approach the empty set, and the intersection will approach the empty set. So what we have is a descending sequence of sets. When n gets larger, E intersect this. We're intersecting with a subset, so we're getting indeed a subset, and a descending collection of sets from this in terms of n. Not only that, when n approaches infinity, the limit of that descending collection of sets is the empty set. So it makes sense to talk about limits of sets, but only when that sequence of sets is ascending or descending. Here they're descending, and the limit, the intersection of all those sets, is the empty set. So if we take the limit of the measure of E set minus this interval, equivalently the limit of the measure of this continuity of measure applies. The limit of the measure is the measure of the limits, but the limit of this sequence of sets is the empty set. So this must equal the measure of the limit, the measure of the empty set, which is 0. So we got ourselves something that when n is large must be little because it has a limit of 0. By the definition of limit of a sequence of real numbers, say, if we make n sub 0 sufficiently large, then we can make the measure of these specific sets, E set minus negative n sub 0 to n sub 0, the closed interval, we can make that less than this given delta. Delta was given. You can make this number less than delta by making parameter n sufficiently large. Definition of limit. So that took care of the wings and the infinite part. Now we're only left with the parts of E that are between negative n sub 0 and n sub 0, including the endpoints. Well, that's just a finite interval. I can certainly take that finite interval and partition it into little subintervals of length less than delta. partition, so deal with the endpoints appropriately, closed on one end, open on the other. But no problem taking this closed and bounded interval and partitioning it into little subintervals. Let's call them I sub 1 through I sub capital N, where the lengths of those little subintervals less than delta. Then we'll take set E. We'll take the unbounded part here. We'll take E intersect I1, E intersect I2, up through E intersect I sub capital N. And then we've taken set E and partitioned it into, in our notation, capital N plus 1, little subsets, each of which has measure less than delta. The measure of this set is less than delta is given explicitly here. And of course, each of these little intervals had length less than delta. So monotonicity, the measure of E intersect those intervals is therefore less than delta as well, as desired. So we've taken set E, partitioned it into a finite number of pieces, each of length, each of measure less than delta for a given delta. Back to the notes. All this previous required was continuity of measure. So this is something we could have done, I guess, as soon as we had continuity of measure somewhere back in chapter 2. But we're going to use that in some of the following stuff. Remember, hypotheses on this was a set of finite measure. We're going to see a fair amount of sets of finite measure in what follows. The next result is kind of an epsilon delta type of continuity of integrals over measurable sets. It deals with some sort of finiteness, not a surprise at this stage. It deals with an integrable function. And basically says if I got an integrable function, then when I integrate over small sets, then we get small integrals. Or in a professional epsilon delta way, specifically it says the following. Let f be a measurable function on set E. If f is integrable over set E, then for each epsilon greater than 0, there's a delta greater than 0 for which. If A is a measurable subset of set E and its measure is less than delta, then the integral over A, the absolute value of f, is less than epsilon. So what it's saying is when you have an integrable function, integrals over little sets are little in a very specific way in the logic of the epsilons and deltas. Converse of that, if we have that set E is finite measures, there's finite measure hypothesis again for the converse. If the measure of E is finite, then in that setting, if for each epsilon greater than 0, there's a delta greater than 0 such that this occurs, then f is integrable. So if f is integrable, you can do this. If set E is finite in measure, and you can do this, equation 26, then f is integrable. So I can take this if and throw an if and only if in around about here. Whoops. Provided E has finite measure. Let's look at a proof of that. Okay. F's a measurable function. F is integrable over set E. We can assume without loss of generality, F is non-negative. Either that or we break this into a positive part and a negative part. Remember, positive and negative parts are ironically both non-negative. Then we'd be dealing with a sum of two functions, and we've got linearity in the appropriate setting. We could consider the positive and negative parts and do an epsilon over 2 argument. So without loss of generality, let's just deal with f greater than or equal to 0. Here's how it would follow in general, positive and negative parts in an epsilon halves argument. So assume f is integrable and let epsilon be greater than 0. That's a setup. Assuming f is integrable, and for every epsilon greater than 0, we're off looking for deltas. All right. By the definition of the integral of a non-negative integrable function, which we have without loss of generality assumed f is, there's a bounded function of finite support, that is a function that's non-zero on a set of finite measure. That's what finite support was. Call it f sub epsilon, for which 0 is less than or equal to f of epsilon is less than or equal to f on set E, and the integral over E of f sub epsilon is really close to the integral over E of f. That is, the difference of the integrals is less than any positive amount you like. Let's use epsilon over 2, so we're doing an epsilon has argument ultimately anyhow. That's because we define this, the integral over E of f, where f is a non-negative function. We define that as a supremum over integrals of these kinds of functions, bounded functions of finite support. I called them effectively class 1 functions, I think it was. So if this integral over E of f is defined as a sup of these things here, as the integrand varies over bounded functions of finite support, which satisfy this inequality, then there's one of these, call it f sub epsilon, that produces an integral that's close to the integral of f. Also, this was defined as a sup, so of course we get all of these to be less than or equal to this one, so I don't need absolute values on this. So in other words, we can find a function, bounded function of finite support, such that the integral of that function is within epsilon over 2 of the integral over E of f. It comes from the definition of integral of a non-negative function. All right. Let's see, here's what we had on the previous slide. We had the difference of these two integrals was less than epsilon over 2. Let's shift our attention to the integral over A of f minus the integral over A of f sub epsilon. All right, both of these are non-negative functions. Both of these are integrable functions. F was integrable by hypothesis. F sub epsilon is a how do we get it integrable? Let's run back and check. How do we get integrability of the f sub epsilon? How about monotonicity? We've got f sub epsilon less than or equal to f, and f is integrable. So monotonicity will give us integrability of the f sub epsilon as well. So both of these are integrable. So I'm justifying taking the difference of the integrals and writing it as the integral of the difference. But I need to figure out what setting we're dealing with. We could do that when we had integrable functions. That was theorem 4.17. We had linearity, additivity as well in this setting of non-negative functions, which this is, remember, f sub epsilon was less than or equal to f. So when we take the difference, we are dealing with a non-negative function. So we can write this as a sum of an integral over A and an integral over E set minus A. So we could add the integral of over E set minus A of this and get an equality here. We're just dropping that from this, producing something larger here. So it's coming out of the additivity in this setting of non-negative functions. We've integrated over a subset. It looks like a monotonicity of, let me choose my words carefully. It's additivity, and we're dropping something that's non-negative. That's where the inequality comes from. Monotonicity had more specific meanings than that. But we get this relationship on the integrals because we've dropped something from the first one. Linearity lets us peel these two apart. And what we've accomplished here is we've moved from integrals over set A to integrals over set E. Linearity we're using is dealing with f and f sub epsilon as integrable functions. So it's this theorem 417 again, that linearity. And we saw on the previous slide that f sub epsilon has been chosen in such a way that the difference of those two integrals is less than epsilon over 2. Okay, remember, we're trying to show this is small. All right, f sub epsilon is bounded. It was a bounded set of finite support. So it's bounded by capital M. So we get f sub epsilon bounded above by m. It was non-negative, so it's bounded below by 0. So if we take a subset of E to be measurable, then the integral over A of f is less than the integral over A of f sub epsilon plus epsilon over 2 That's simply taking this to the other side of the inequality here. We've got this function f sub epsilon bounded by m, and we're integrating over set A, which has, I don't know, measure of set A. So we get the integral bounded by capital M times the measure of A plus epsilon over 2. We're trying to make this small. We were given epsilon. We still get to choose. We still have to choose delta. And there's a big hint at what to choose delta for right there. So we're leaving off with the integral over A of f is less than or equal to m times the measure of A plus epsilon over 2. We're trying to pick delta to make the measure of A sufficiently small. Won't make it sufficiently small, so this gives you the other epsilon over 2. So define delta to be epsilon over 2m. Then the measure of A less than delta, which we're choosing to be epsilon over 2m, implies that previous inequality we had m times the measure of A. Well, we've got the measure of A less than epsilon over 2m. Stick that in here. The m's cancel. There's an epsilon over 2. There's an epsilon over 2. And there's your epsilon. And we were trying to show that the integral over A of f is less than epsilon, provided A has measure less than delta. There's the delta to choose. It was based on f sub epsilon, which in turn was based on the choice of epsilon, as we'd expect. Now, for the converse, we want to show if all that epsilon delta stuff happens, then function f is integrable, with the added assumption that E has finite measure. So suppose E has finite measure. Suppose that epsilon delta stuff holds as given in equation 26, using the book's notation for that equation. We can choose epsilon to be anything. Let's anchor it at 1. Let epsilon be 1. Let delta sub 0 be a corresponding delta that's guaranteed to exist under the assumption that that equation 26 stuff or implication 26 stuff holds. Now, hey, the measure V is finite here. Lemma 4.22 applied to finite measure sets and said you can cut them into a finite number of pieces, and all those little pieces will be small in measure. By lemma 4.22, since E is finite in measure, E is a disjoint union of a finite collection of measurable sets. Let's call them E sub k equals 1 to capital N. And each of these E sub k's is of measure less than, you name it, I name it as delta sub 0, the delta that we had upstairs. Then, if we integrate over E, the absolute value of f was not necessarily non-negative in this converse part, right? So we're introducing that. Integrate over E, absolute value of f. We just wrote E as a disjoint union. Additivity from the appropriate setting. Looks like the setting here where the absolute values is non-negative functions. So linearity additivity lets us treat this integral over the union as a sum of the integrals over the pieces, the E sub k's, they're disjoint. And we had made this using implication 26. We had made this less than epsilon, and we chose epsilon to be 1. So we get this to be less than 1. We're summing from 1 to n. That gives out a capital N. Capital N is some fixed number. It was produced based on set E and lemma 4.22. It's the number of pieces that we broke it into. But that's simply a function of set E. We get this finite bound. Integral over E of the absolute value of f is less than this bound. So f is integrable over set E. That's what integrable means. The integral of the absolute value is finite. So there's the converse. Okay, we're going to become enamored with this condition. This is related to the uniformly integrable that was mentioned in the definition or the title of the section. So the following definition requires that this thing here, 26, hold uniformly. That is, for any epsilon greater than 0, there's a delta that works for all The for all, when you hear uniformly, it's sum for all. It's going to hold for all functions in some set. The book's going to use the term family instead of set. I don't know why they do that. But we're going to get this desirable property to hold throughout some family of functions. And we're going to call that behavior uniform integrability, uniformly integrable. A family, calligraphy F, of measurable functions on set E is uniformly integrable over set E, also called equi-integrable. We'll call it uniformly integrable, provided for all epsilon greater than 0, there's a delta greater than 0, such that for each, there's the uniform part, for each function in this family, if A is a measurable subset of E of measure less than delta, then the integral over A of the absolute value of F is less than epsilon. Again, for all F in that family. So it's the family that's uniformly integrable. For us, the family will be, in practice, a sequence of functions. It could be something bigger than that. Consider the following example to illustrate uniformly integrable. If we have a certain type of boundedness, say on that family of functions, calligraphy F, we can get uniform integrability. Suppose G is a non-negative integrable function over set E. Define the family F to be all functions that are measurable on set E and an absolute value are less than or equal to G on set E. Now, monotonicity will tell you the integral over A of the absolute value of F is less than or equal to the integral over A of G. Monotonicity looks like here in the setting of non-negative functions. G is non-negative, we said that. Absolute value of F, of course, is non-negative. And we have the inequality right here. So monotonicity will give this. We need to be able to make that small. Well, you can. Proposition 4.23 applied to function G says, hey, G's integrable. So apply proposition 4.3 to G. I can make the value of this integral small, less than epsilon, by making the measure of set A sufficiently small, less than delta. So we can do the same thing for all of those functions F by the monotonicity. So potentially quite a gigantic collection of functions here in that family. Like I said, we're mostly interested in sequences because we're going for convergence there. First result about uniform integrability, a really easy one actually, just applies to a finite collection of functions. Let f sub k equals 1 to n be a finite collection of functions, each of which is integrable over E. Then the finite collection is uniformly integrable. Easy enough. Since we know that since each of the f sub k is integrable over E, proposition 4.3 tells us there's a delta. So for each f sub k, there exists, say, a delta sub k. Such that if we choose a measurable subset of set E and the measure of that set is less than delta sub k, then the integral over A of f sub k is less than epsilon. Proposition 4.23 applied to function f sub k. All right, do that for all n of those functions, giving you a delta 1 through delta sub n. Let delta be the minimum of those. Then, provided the measure of A is less than delta, then, for example, it's less than or equal to delta sub k, because we chose delta to be the min of those, then we'll get the integral over A of the absolute value of f of sub k less than epsilon. Set A has sufficiently small measure for this to happen. It needed to be measure less than delta sub k. It is, it's less than delta, which in turn is less than or equal to delta sub k. So we're good with that. And that gives the uniform integrability of that finite collection of families. Can extend this, right, to an arbitrary collection. If I have an infinite number of deltas, then I can't take a min. I'd have to take an inf, and I might not get delta positive. So of course, that's where this falls apart if I try to mimic this in an infinite setting. But finite collection of integrable functions forms a uniformly integrable family of functions. Now let's shift our attention to a convergence theorem. So the convergence theorem will come in two steps. We'll make a claim about integrability, and then we'll make a claim about the value of the integral. So we'll explore properties of uniformly integrable families and give a convergence theorem that applies to uniformly integrable sequences that converge pointwise of functions. Proposition 4.25 says, assume E has finite measure. So there's that hypothesis that will carry along from ultimately the converse here. Ultimately 4.23 is where we're going to use that, if memory serves. But this result requires finite measure. In fact, in one of the exercises, problem 4.41, you're to show that this doesn't work if we don't have the finite measure hypothesis. It does not hold for infinite measure sets E. But we're taking E to have finite measure. Let the sequence of functions, f sub k equals 1 to infinity, be uniformly integrable over E. If f sub n converges to f pointwise almost everywhere on E, then f itself is integrable. So it's a conclusion of integrability of the pointwise limit function of a collection of functions which is uniformly integrable, to throw around the lingo. All right, first off, f sub n approaches f pointwise almost everywhere. F is measurable. I guess that's always looming in the background, but a pointwise limit of measurable functions is measurable. So we've got f measurable. Question is it integrable? All right, we'll take epsilon to be 1. We've assumed uniform integrability of this family of functions here with epsilon equals 1. Take a corresponding delta, let's denote it delta sub 0, such that implication label 26 holds. For this epsilon, there exists a delta such that, A is a measurable subset of set E, and the measure of A is less than this, then the value of the integral will be less than that, less than the epsilon value. So let epsilon be 1. We're assuming uniform integrability. So for all epsilon, blah, blah, blah. E has finite measure. So lemma 4.22, I guess we go all the way back to lemma 4.22 with a finite measure stuff. Then we can express set E as a disjoint union of a finite collection of measurable sets. And we can make each of those sets have measure less than this delta sub 0. And there's only a finite number of them, of sets. So we can use additivity. Of course, additivity doesn't apply to infinite sums, only to finite sums. Additivity always means, additivity in the sense of integrals always means finite additivity. We did have some other behaviors related to series, but additivity, that term always means finite sum. By the additivity from the appropriate setting, it looks like we're dealing with non-negative functions here. If we'll integrate over E, f sub n, absolute value of, that's the same as integrating over this little finite union of the E sub k's, because we've partitioned up set E because it had finite measure. We get that finite partition there. By additivity, when we have a finite collection here, we can write it as a sum of the integrals over the constituent sets over each of the little E sub k's. And we've chosen the E sub k's to be sufficiently small, less than delta sub 0, such that an integral over those sets of the absolute value of f sub n is less than epsilon, and epsilon equals 1. So the E sub k's are playing the role of set capital A that we had previously in the definition of uniform integrability. So we've chosen it in such a way that each of these is less than 1 in value. Sum those up to capital N. So we get this capital N as a bound on the integral over E of each of the f sub n's. All right. I think each of the f sub n's are going to be integrable. It's showing f is integrable that we need. So we need to take a limit. The limit of the absolute value of the f sub n's is the absolute value of f. Fatu's lemma applies to tell us, so we don't necessarily have convergence. Right, we've gone through the f sub n's. Well, we do have pointwise convergence. We're applying Fatu's lemma, so we need to take some limits. We'll take a lemit here. The integral over e of the absolute value of f is less than or equal to the lim of the integral over e of the f sub n's. Fatu's lemma. Fatu's lemma applied to non-negative functions, wasn't it? And we had this bound n on all the integrals of the absolute values of the f sub n's. So the lim inf has that bound as well. It's less than or equal to n. And there's the integrability of f. So the integral over e of absolute value of f is less than or equal to n. N arising out of partitioning that set of finite measure. So I see big time, here it is, where the finite measure of set E plays a role, and the use of lemma 4.22. So we get integrability of the absolute value, and that implies integrability of f. It's a definition of the integrability of a function f, is that its absolute value is integrable, finite values for integrals. Okay, so we're just about set to prove the convergence theorem. And the convergence theorem, the Vitali Convergence Theorem, deals with a sequence of functions on a set of finite measure that are uniformly integrable. Let E be a finite measure. Suppose the sequence f sub n is uniformly integrable over set E. If f sub n approaches f pointwise almost everywhere on that set, then first claim, f is integrable over set E, and the limit of the integral is the integral of the limits. Okay. Oops. Vitali Convergence Theorem. Let's go through the proof. It's not terribly lengthy. We had the integrability already, right? The previous thing we showed established the integrability of that, proposition 4.25 for the record. So we have an integrable function. Proposition 4.15, you know what, let's look at proposition 4.15. So we're about to use it a couple of times over. I just happen to have it here. It says if a function is integrable, then that function's finite almost everywhere. And you can throw out sets of measure 0 and not change values of integrals. We're dealing with a situation of integrable and convergence almost everywhere. So we're going to tweak that a little bit using this proposition. So integrable implies finite almost everywhere, and that I can throw away sets of measure 0. Okay. Proposition 4.15 implies f is finite almost everywhere. Okay, that we just saw because f is integrable. Also, we can excise a subset of E of measure 0. Let's throw out the one where pointwise convergence doesn't hold. We had almost everywhere pointwise convergence. All right, so there's a set of measure 0 in which you don't have pointwise convergence. Throw it out. That won't affect values of any of these integrals. So without loss of generality, we can toss out places where we might have to deal with the infinity stuff and places where we might not have pointwise convergence. Both dealing with sets of measure 0. Throw them out. They don't affect values of integrals, 4.15. And without loss of generality, we can say our limit function is real valued and that we've got the convergence pointwise throughout set E. All right. For any subset of set E, measurable subset of set E, and any natural number, we have the following. So we want to make things small. Right? We're trying to show the limit of this as n approaches infinity is that. So we want to make this small first to set up. The absolute value of the difference, well, each of these are integrable. The f sub n's are integrable, uniformly integrable family, and f is integrable by the previous result, proposition 25, wasn't it? So by linearity applied to integrable functions, the difference of the integrals is the integral of the difference. All that happens within an absolute value. You can take that absolute value in the integral by the integral comparison test was it allowed us to do that kind of computation. We can break this up. Set E can be partitioned into set A and its complement, E set minus A. So break that into those two disjoint pieces. Additivity from the appropriate setting, looks like non-negative functions here. We can write that as a sum additivity because the two sets, E set minus A and set A, they're disjoint. We get the equality between those. We can apply, let's see next, triangle inequality pointwise here. Absolute value of f sub n minus f pointwise is less than or equal to the absolute value of f sub n is the absolute value of f pointwise. That is, pick a particular x value. You get this evaluated at that x value less than or equal to this plus that evaluated at that x value. Regular old triangle inequality for real numbers. You get a relationship between these two integrands, that one being less than or equal to this one, pointwise. Monotonicity then kicks in to say, okay, the integrals behave in the same way. And linearity from the appropriate setting lets us break this into a sum of integrals. Okay, so we've got the difference here less than or equal to the sum of these three things. We're going to make each of these less than epsilon thirds. So that's the last computation. And we will do so by making, in particular, we have to make n sufficiently large. These two are affected by that. All right, so let epsilon be greater than 0. We hadn't chosen it yet. The uniform integrability says we can pick a delta such that the integral over a of the absolute value of f sub n is less than epsilon over 3. So there's one of the epsilon over 3s. Uniform integrability on this piece, we still haven't chosen the n, have we? Provided set A is sufficiently small in measure. Definition of uniform integrability on the f sub n's. All right. Fatu's lemma, we have the f sub n's approaching f pointwise, as does the absolute values. Integral over a of the limit function is less than or equal to the lim inf of the integrals. Well, each of these is bounded by epsilon over 3. So the lim inf is bounded by epsilon over 3. So the integral of the absolute value of f is bounded by epsilon over 3, and we're 2/3 of the way there. So we've got an epsilon thirds on the integral over a of the absolute value of f sub n. We've got it on the integral over a of the absolute value of f itself. Now we're still left with, so let's go back. We got this part and this part. Each of these two pieces we have less than epsilon over 3. It's this thing here we need to deal with now. So absolute value of f sub n minus f. We need to deal with that, and we need to make that small. Well, f is real valued, set E has finite measure. Okay, we're going to use something else that requires finite measure. Egoroff's theorem, remember Egoroff's theorem, says real valued functions on sets of finite measure. Pointwise convergence is nearly uniform convergence, to paraphrase Egoroff's theorem. That is, there's a set E sub 0, a subset of set E. We can make its measure small as you like. Let's make it less than delta, such that we get uniform convergence if we throw away that little set. So we're getting uniform convergence nearly everywhere. We're throwing out this set of small measure, not a set of measure 0, this set E sub 0 of small measure. All right, so uniform convergence, that means, remember we needed to choose an index sufficiently large. Here it comes. That means if we make the index n sufficiently large, that is, there's a capital N, a natural number, such that when the index lowercase n is greater than or equal to capital N, this can be made small throughout the appropriate set, the set E set minus E sub 0. Let's make it epsilon over 3 times the measure of set E. So we can make it as small as you like. I want to make it that small. The epsilon shouldn't be a surprise. The 3 shouldn't be a surprise. The measure of E might be a wee bit of a surprise. But epsilon thirds is what we're going for in this. So with the index sufficiently large, we get this bound, and that'll allow us to put a bound on that integral. Okay, here's where we left off a couple of slides ago. This we had less than epsilon over thirds, uniform integrability. This we had less than epsilon thirds, was Fatu's lemma combined with the uniform integrability. And we had just chosen n to be sufficiently large up here that the absolute value of f sub n minus f was less than epsilon over 3 times the measure of E. So we've got this constant bound on this. That allows us to put a bound on the value of the integral of the upper bound on the function times the measure of the set over which we're integrating. It's E set minus E sub 0. Well, we can cancel this and produce, I don't know how big this set is, but certainly the measure of E set minus E sub 0 is less than or equal to the measure of E. So what we're producing here is something less than epsilon over 3 ultimately. So we get out a less than epsilon over 3 here, here, and here, producing a sum that's less than, ultimately less than epsilon. And that's what we were trying to show. So make n sufficiently large using the uniform integrability. We produced all this other stuff, and then the n sufficiently large, then the distance between these two things, an absolute value, is less than epsilon. That simply means this sequence of numbers, remember definite integrals are simply numbers, equals this real number. That is, the integral over E of f sub n approaches the integral over E of f itself. That's a convergence theorem. So there's the Vitali convergence theorem. And it's based on this idea of uniform integrability. That's a constraint. Geez, this really catches my eye. That's quite a constraint there as well. It only applies on sets of finite measure, and you see why. Underlying the proof was that thing where we cut a set of finite measure into little pieces, little disjoint pieces, little as you want. In a sense, the next note says some informal ideas. The Vitali convergence theorem swaps the domination given in the Lebesgue dominated convergence theorem for finite measure and uniform integrability. Lebesgue dominated convergence theorem, we had an integrable function g that dominated all the functions in the set. Yeah, we're kind of getting that as well. In some sense, we're getting boundedness with this uniform integrability. This is implying some kind of boundedness or some kind of integrability that's holds throughout uniformly. Next result shows that the uniform integrability is necessary in the Vitali convergence theorem, at least in some particular case. So in general, we can't eliminate the uniform integrability. What theorem 4.26 says is, let E be a finite measure. Suppose H sub n is a sequence of non-negative integrable functions that converges pointwise almost everywhere on E to the 0 function. All right, if we have uniform integrability, the Vitali convergence theorem tells you the integral of the limit function will be the limit of the integrals. Well, this says we get the limit as n approaches infinity, the integrals is the integral of the limit function, which is 0, if and only if H sub n is uniformly integrable. So half of this, piece of cake, half of it is the Vitali convergence theorem. If you have the uniform integrability stuff, the limit of the integrals is the integral of the limit function, and the limit function is a 0 function. So that's where this 0 comes from, Vitali convergence theorem. The other half is if we get the value of this limit to be 0, then we must have uniform integrability. So let's go through a proof of that. Yeah, if we have uniform integrability, Vitali's convergence theorem tells you the limit of the integrals is the integral of the limit, and we said pointwise this converges to the function that's identically 0 on set E. So integrate the 0 function, get 0 out, there's that first half. For the converse, we need to suppose the limit of the integrals of the h sub n's is 0. Then we need to show we got the uniform integrability. So let epsilon be greater than 0. We go looking for deltas to get the uniform integrability. Since the limit of this sequence of numbers is 0, these are integrals of non-negative functions. The h sub n's, they were non-negative functions. So all these integrals are finite numbers. These were integrable as well. So we've got these bounded below by 0. I don't need an absolute value around this. In other words, the limit of these being 0 means you make the index sufficiently large. We can make these less than epsilon for a given epsilon. Definition of limit of a sequence of numbers equals 0, a sequence of non-negative numbers in particular. Each h sub n is greater than or equal to 0. Yeah, they were non-negative. So if we choose a subset of set E, measurable, we haven't put any constraint on set A yet. We'll get, in general, we'll get the integral over A of h sub n is less than or equal to the integral over E of h sub n. And if we make n sufficiently large, we know we can make these less than epsilon. So with n sufficiently large, no matter what subset of E you choose, we'll get this kind of relationship here for n sufficiently large. In particular, the integral over A of h sub n is less than epsilon. Equation 30, the book's notation. All right, we're trying to extract uniform integrability. Proposition 4.24 says, since these h sub n's are integrable, then a finite collection forms a uniformly integrable collection. Previously, on the last slide, we said if the index was sufficiently large, let me bounce back to the last slide. The index was sufficiently large, greater than or equal to capital N, we got this kind of behavior. That's good behavior for uniform integrability. That was everything except h1 through h sub capital N minus 1. Well, that's a finite collection. Each of those is integrable, so they form a uniformly integrable collection because there's only a finite number of them. So we're in good shape to get uniform integrability. For given delta greater than 0, let delta greater than 0 correspond to the epsilon. For the set in the definition of uniform integrability to satisfy the less than, let delta be greater than 0 correspond to epsilon greater than 0 for this set, in the definition of uniform integrability. That is, you'll get integrals over set A to be less than epsilon, provided the measures of A are less than delta on this set. So we'll get integrals of these functions to be over sets A, satisfying the conditions given in uniform integrability. We'll get these to be less than epsilon. The first ones we had on the previous slide, when the index was sufficiently large, we had those having integrals less than epsilon regardless of what set A was. Let's go back. Yeah, we had the integral over A of h sub n. We had these less than epsilon, provided n was sufficiently large. Came from the definition here. So we've got these less than epsilon by making the index sufficiently large. We've got these having integrals less than epsilon using the uniform integrability that comes out of proposition 4.24 because this is just a finite collection. So welcome to analysis. We trap the infinite amount sort of on the sides, as we did with some of the other stuff. And then with the finite part that was left over, we dealt with that, in this case, with proposition 4.24. Finally, wrap up chapter 4. This result doesn't hold if you drop the assumption of non-negativity of the h sub n's, is to be shown in one of the problems. Now this uniform integrability, we're going to explore it a little bit more in section 5.1, and we're going to see a lot of the stuff we did, the convergence theorems we did, required various hypotheses and pointwise convergence. Turns out those various hypotheses can be replaced with uniform integrability. And each of the convergence theorems we've had, they're going to hold when we have uniformly integrable pointwise convergence sequences as well. We'll show a little bit of that. Actually, in section 5.1, we'll prove this, and then we'll elaborate on that, but not go through proofs of all of that stuff. It's left as exercises in the book. But uniform integrability might be a little bit more powerful than you initially think, as we'll show in the next section. So that concludes chapter 4. We got 3 more sections in chapter 5 I want to go through, and that'll conclude real analysis 1. Have a nice day. I'll see you in chapter 5 soon. Bye-bye.